Hello, everyone. Welcome to the Data Science Seminar from the University of Washington eScience Institute. As part of the University of Washington, we acknowledge the Coast Salish peoples of this land, the land which touches the shared waters of all tribes and bands within the Suquamish, Tulalip, and Muckleshoot nations. It is my pleasure today to introduce our speaker, Dr. Tanya Harrison. Tanya is the Director of Strategic Science Initiatives at Planet. Prior to this, she spent over a decade working in science and mission operations for multiple NASA Mars missions, including the Opportunity and Curiosity rovers and Mars Reconnaissance Orbiter. She holds a PhD in geology from the University of Western Ontario, a master's in Earth and Environmental Science from Wesleyan University, and a bachelor's degree in astronomy and physics from the University of Washington. Today, Tanya will talk about Planet and its products, as well as data access through NASA Commercial SmallSat Data Acquisition Program. As usual, please the Q&A feature of our Zoom webinar to ask Tanya any questions you may have at the end of the presentation, if possible. And with that, I would like to invite Tanya. Thank you.
Great. Thanks so much, Nicoletta. And thank you everybody for dialing in. It looks like we have a really good audience today. So as Nicoletta said, I'm Tanya Harrison, and today I'm going to be talking about an introduction to Planet if you're not familiar with the company and our satellites, as well as how you can access data for free using the NASA Commercial SmallSat Data Acquisition Program, which is a little bit of a mouthful, so we'll call it SISDA for short. So if you're not familiar with Planet, Planet is an Earth-observing satellite and imagery company based in San Francisco with the mission of imaging the whole world every day to make change visible, accessible, and actionable. And we do this through two sets of constellations of satellites right now. The main one that we're most well known for is the PlanetScope constellation, and this is comprised of our CubeSats that are 3U, so they're about this big. And they image the whole landmass of the world on a near daily basis. They're essentially on anytime they're flying over land. So these are taking a daily background scan at 3 to 5 meter resolution. The older satellites were 4-band, so RGB and near infrared. The newer satellites are 8 bands, which still go through RGB and near infrared with a few extra bands put in the middle there. Then there's about 200 satellites in that constellation. Then we have another constellation called SkySat, and this is more of your traditional tasking satellite constellation. So you have to specifically target where you want to take the images. We have 21 of these. They can image anywhere on the world up to about 12 times a day, depending on latitude. And they image at 50 centimeter resolution in RGB, near infrared, and panchromatic bands. You can also do stereo imaging and full motion video from space with these satellites as well. This is just a little bit of an overview of the two constellations. So why do we image the whole world every day? Well, I think this audience probably knows that the Earth is really cloudy in certain places during huge extents of the year, including Seattle, but also the rainforest. So this is an example of 1 month of coverage from Landsat and Sentinel-2. And you can see there's a lot of cloudy images, a lot of days where there's just no coverage whatsoever. But if we compare that to 1 month of coverage from PlanetScope and SkySat combined, you still have a lot of clouds because there's nothing we can do about that in terms of optical imaging, but it gives you a lot more chances to see through the clouds or around the clouds if you're at least trying to image the whole world every day. So let's take a little bit of a deeper dive into the PlanetScope constellation. You might also hear these referred to as the Dove satellites or the Super Dove satellites, depending on what generation of the Doves we're talking about. These are really inexpensive satellites. We build them using a lot of commercial off-the-shelf parts to leverage R&D from other industries. And so in the course of 6 years, we had 14 different builds of these satellites. So each version that we launch is called a flock. So you can see like what changes we've made over time based on what flock of satellites you're looking at. These are meant so that we can do rapid upgrades and iterations over time rather than getting stuck with a single design for the course of multiple years. And we just replenish the constellation over time. So the satellites are designed to deorbit and burn up in the atmosphere, and we replace them with new and improved satellites every few months or so. Usually we launch with SpaceX, but we've also launched with Rocket Lab, ISRO, the Indian Space Agency. Way back in the day, we launched some satellites with Russia, but right now, mostly we launch with SpaceX. In total, this coverage comes out to about 4 million images a day, or about 30 terabytes of data that we downlink across 48 different ground stations around the world. So it's quite a lot of data for us to handle. It's all stored on the Google Cloud. We've done 32 launches so far successfully, and we've got another one coming up relatively soon. So stay tuned for the announcement of that one, in case you want to watch it live online. So I mentioned that we've had multiple generations of the Dove satellites over time. The initial ones that we launched were the Dove pilot satellites, and these were actually launched from the International Space Station. So they were in an ISS orbit. And these were 3-band RGB imagers that had what's called a bare pattern filter on them. And this is the same kind of filter that you would find in your consumer digital camera at home. It's meant to mimic human vision. This is great, but it doesn't give you the most scientific information in your imagery. So we upgraded to the Dove Classics, which comprised most of the constellation for the last few years, by changing to a split frame imager where half of it was that RGB bare pattern filter and the other half was near infrared. So you could start to get information about things like vegetation health. Then we changed the sensor again in the Dove R or Dove Refresh set of satellites. There were about 25 of these in the constellation. And we changed to a butcher block filter to, short version, get kind of better performance all around. The images are sharper, the dynamic range is better, the color is better, the bands are tightened up compared to the older satellites, and we'll see a plot of that on the next slide. Just all around much better performance. And then we kept that type of sensor layout when we made the next upgrade to the Super Dove satellites, which make up the entire currently operational constellation. So none of the older satellites are still collecting data. Most of them have been actively deorbited at this point. But we added a coastal blue band, a second green band, a yellow band, and a red edge band, in addition to the 4 bands that we had before. And we did this to try to make the data more interoperable with Sentinel-2. So if you look at the bands from Dove Classic, you can see they were pretty broad and the peaks were blue shifted relative to what you see in Sentinel-2. So we worked to shift those band centers over time to make it so that the data plays more nicely with each other. So the data is designed to be interoperable with public data sets like Landsat and Sentinel. You have the option now of actually harmonizing all of your data to Sentinel-2, whereas our older data was previously harmonized to RapidEye, which was a constellation that we operated through early 2020 from a company called Blackbridge that we acquired a few years ago. But now you can use all of these data sets together. So here's just some examples of some things that we've imaged on the surface of the Earth over time with the satellites. I'm sure you saw the news stories earlier this year about the massive volcanic eruption in Tonga. We were actually actively monitoring this volcano already for some researchers at NASA Goddard, led by Dan Slayback, because he had noticed some volcanic activity in the area and said, hey, I think there might actually be something going on. Could you make sure that this island is getting imaged? So this was a view that we had on November 17th of 2021. And if we fast forward to early in 2022, before the big eruption, there had been a lot of volcanic activity that built up this central part of the island. And so we actually caught the buildup, we caught some venting in progress. And then a few hours before the massive eruption, there was actually a slightly smaller eruption that didn't really make quite as much news coverage, but that eruption took out the central part of the island, made it so that the caldera was now underwater. And that's what led to the larger eruption being so explosive, because now you had this occurring underwater. And so this was the after image that we caught after the clouds and the ash had dispersed. You can see that the central part of the island is completely gone now. This eruption not only triggered a bunch of ashfall on the surrounding Tongan islands that we captured with both PlanetScope and satellite imagery, but it also ended up causing oil spills along the coast of Peru, about 6,000 miles away. These are some views of an active lava flow in La Palma in Spain from late last year. And if you throw in the near infrared band, you can actually start seeing things like the glowing lava moving through here. And if we take another look at some of this eruptive activity, you can actually see the smoke coming off of the lava where it's entering the water. Another reason to image the whole world every day is the world is changing very rapidly, constantly. So this is an example from February of last year in Western Australia on February 1st versus February 2nd. So we have a lot of folks that use this data to track the effects of wildfires over time. And here's a series of images over the course of 3 days from April of last year, looking at farming in India. The changes are very small, but if you look really closely, you'll see. So here is April 25th, 26th, and 27th. So let's get into some actual examples of science done with planet data from the research community around the world. We have a few different science programs that provide data access pathways for researchers, depending on what your affiliation is and where you're based geographically. And across all of these programs, we have over 20,000 registered users. These users have produced over 2,000 peer-reviewed publications and conference presentations using planet data. And they consist right now of users at over 100 universities worldwide, including University of Washington, and about 30 US federal civilian agencies through the NASA program that we'll talk about later in this presentation. In addition to NASA, we have partnerships with the European Space Agency and DLR, the German Space Agency as well, and then some other smaller partnerships with different countries and different government agencies. And from just the NASA program alone, researchers have downloaded over 5 times the entire landmass of the Earth in square kilometers. So scientists are really good at consuming a lot of data to try to understand the world. This is an example where NASA actually reached out to us at Planet to say, hey, the Milne ice sheet collapse off the northern coast of Ellesmere Island in Canada is something that we tried to see if we captured in Landsat imagery, but the images were cloudy. So we were wondering if you managed to capture anything. Because we have so many satellites in the Planetscope constellation, they actually get crowded in the higher latitudes. And so when you're up in the Arctic, you can have not only daily coverage, but sub-daily coverage. In this particular case, we had 4 separate satellite passes on July 30th. 3 of them were cloudy and the 4th one was clear. And so the after image here where you can see the breakup was the clearest atmosphere view that we had of the collapse. We also had multiple satellite passes from the previous day, and looking through the clouds, you could actually constrain the time period of the collapse to within a 10-hour time period. And looking at the imagery in the days leading up to the collapse, you could actually see things like melt ponds starting to form on top of the ice as a signal that maybe something was going to happen here. This is work by Sarah Cooley, who was at Brown University. Now she's at the University of Oregon. And she did research using 70,000 plus dove images to track near daily changes in water extent using machine learning across huge swaths of Alaska and northern Canada to see how these might be contributing to greenhouse gas emissions into the atmosphere because of melting permafrost in the areas. Her research showed that in some areas, these lake shorelines were fluctuating a lot more than previously recognized, which suggests that these lakes might be emitting more greenhouse gases than previously thought. And from this, she made these maps of lake dynamism across these large areas. And so we could actually look and see how much are these changing over time across different parts of the Arctic. This is another event that made news around the world, and some of the folks that worked on this I see are on the call right now. In February of last year, there was a massive flash flood in the state of Uttarakhand in India, which killed dozens of people and washed away a couple of hydroelectric power stations. This is an area of the world that experiences a lot of flooding and landslide activity because you have a lot of steep slopes. But in this case, there was some confusion as to what actually triggered this flood in the first place. The initial reports that came out suggested that this might be a glacial lake outburst flood, but completely by chance, we had 2 dove satellites that flew over this area 27 minutes apart. The first one caught the dust cloud being kicked up by the flood moving down the valley 10 minutes after the flood started. And the second image was 27 minutes later, after the first hydroelectric power station had been destroyed, but before the second one had been destroyed. And from this, researchers were actually able to look upslope and try to figure out what the cause of this flood was. And this is that 27-minute time sequence. So this here is that dust cloud getting kicked up. The first power station was around here, and the second one is around here. So if we look at that again, you can see the first one, the dust cloud hasn't reached this part of the slope yet, and the second one, it's all the way over here. Since these images go out basically as soon as we finish processing them through our interfaces like Planet Explorer, which is our graphical user interface for downloading the data, we'll often have researchers analyzing stuff in near real time and posting their analyses on Twitter. So Dan Sugar at the University of Calgary is probably one of our most active researchers in terms of posting things on Twitter whenever there's news of a landslide somewhere. And so he was posting saying, this doesn't look like a glacial lake outburst flood, despite what news reports were saying from what they're seeing on the ground. And so he starts tagging in other scientists. They start giving their commentary. Folks brought things like video from on the ground into the thread. People started posting things like combining data with SRTM data so they could get three-dimensional views of what was going on. So it's really amazing to see this kind of analysis evolve in near real time when you're talking about disasters like this. And so Dan and some other folks reached out to us and said, hey, could you get SkySat imagery of what we think is the source region for this flood? And this is the image that we captured. And it was pretty obvious what the triggering location was. So here you can see where you had this slope detach. So what happened was you had a glacier detach from the slope here. It fell almost 2 kilometers straight down into the valley floor, melted, and then all of that water mixed with the debris on the valley floor and then flowed down slope and ended up causing all of the damage. I mentioned before that we also had a constellation called Rapid Eye. This was a set of 5 satellites that operated from 2009 through the end of 2019 into a little bit of early 2020 that imaged certain parts of the world at 6.5 meter resolution in RGB, red edge, and near infrared. Even though we're not collecting data with this constellation anymore, there's still a lot of publications coming out using this data, and it provides some continuity with the PlanetScope data, which doesn't really kick in until 2014. In this work, researchers at the University of Waterloo were looking for groundwater discharge points in the region, which could signal areas for danger of waterway contamination because of active shale oil exploration in the area. And so from this, they looked for recurring icings that might be sourced by groundwater springs, and they were able to map those out in the 6.5 meter Rapid Eye data. So they could definitely continue doing this work moving forward with the PlanetScope data, since you're looking at 3 to 5 meter resolution instead. We also have a lot of people doing forestry work with our data, partly through programs like our agreement with the Norway's International Climate and Forest Initiatives, or NICFI. And this is a program that makes tropical base maps, which are cloud-free, gap-free mosaics of our data created over weekly, bi-weekly, monthly, and quarterly cadences. These are made freely available to anybody that are studying deforestation and forest conservation efforts. And so these are hosted in Google Earth Engine, so people can do a lot of broad scale analyses with them. In this case, a team of researchers spanning the US, Spain, and Portugal evaluated forest mortality patterns in a specific part of Brazil containing eucalyptus trees using these base maps made available through the NICFI program. And they looked at these changes over time to make these probability of mortality maps. So from this, they could look at how tree mortality might be affected by different drought conditions in the area. This was a really novel application that I didn't expect to see with our data, because the wavelengths that we image at are not designed to do any kind of atmospheric science. But this group out of Duke University combined PlanetScope data with ground-based measurements of particulate matter smaller than 2.5 microns, or PM2.5, to create maps of air quality in different cities around the world. Usually, this is something that involves using aerosol retrieval products that have resolutions of less than 1 kilometer. And air quality monitoring stations themselves are really expensive to build and also to maintain over time. So this group sought to create a more cost-effective approach to mapping out ground level 2.5 values. They used a machine learning algorithm. They used a convolutional neural network to basically look at how hazy PlanetScope images were and combined that with corresponding ground-based measurements taken on the same day from air quality monitoring stations in Beijing across 35 different areas. They looked at color changes in things like the fields and the color of buildings over time as sort of that marker of haziness, and then used that to train their model. They then ran the model over Shanghai without incorporating any of the ground-based data to look at the results there, and then compared the model results to the actual ground-based measurements. And they were able to get very good results from their CNN compared to the ground station results. They've now taken this and they've started running it over different cities in India. I believe they were looking at Mumbai and New Delhi in their new paper, if I recall correctly. So this is a model where you could theoretically take this approach over any city that looks visually similar to the cities where they've trained these models over. So the buildings have to have kind of the same color patterns. It might not work very well over something like an older European city where maybe the roofs are dominated by, red buildings. Whereas in looking at something like Beijing or Shanghai, you have a lot more modern buildings. And so you're looking at things like color variations in white and blue and gray of the buildings for a lot of this change detection. But it is a method that they're looking at expanding into different areas. So from this, they were able to create near daily 200-meter spatial resolution maps of PM 2.5 levels across these broad areas over Beijing and Shanghai. So I mentioned before that our base map products are these cloud-free, gap-free mosaics that we make over certain time periods. We can make custom ones as well with either the PlanetScope or the SkySat data. And back in the early days of COVID, NASA Harvest, which is the food security arm of NASA run out of the University of Maryland, approached us because they had been approached by the government of Togo to create a countrywide map of cropland because they were concerned that the supply chain shutdowns from COVID were going to impact food production in the country. And so they wanted to proactively distribute aid to try to make sure that there wasn't going to be a famine from these shutdowns. From the day that Harvest approached Planet saying we need a map, to the day they delivered it to the government took 10 days. This was a huge lift on the part of both Planet and NASA Harvest. But we created a 72-centimeter SkySat base map of the entire country of Togo. It helps that Togo is quite small, so we were able to create a map without using too many images. But we also had images over the growing season, which was very critical for creating a map of cropland, because obviously you're not going to catch all of the cropland areas if you're not looking at it when the crops are active. So from this, they did a bunch of hand labeling, over 1,300 hand-labeled examples. They combined that with a crowdsourced publicly available data set of about 36,000 labels of cropland versus not cropland globally, and then used this to create their model. And these are results that they got from the SkySat imagery compared to 30-meter and 100-meter publicly available data sets. I said before the SkySat imagery is 50-centimeter resolution. We actually lowered the orbit altitude of the entire constellation about a year and a half, 2 years ago now, to increase the spatial resolution of the imagery. So the older data you will see is at 72 centimeter to 1 meter, and then the newer imagery is at the 50-centimeter range. You can see here that you're picking up a lot more cropland in the higher resolution imagery, which is really critical in areas like Africa, where you have a lot of smallholder farms, because these are obviously smaller than the resolution limits of the 30-meter and the 100-meter data in a lot of cases, like you can see here. They also tend to be very irregularly shaped, so they don't look like round pivot irrigation fields like you tend to see if you're flying over the Midwestern United States, for example. So being able to pick up these small crop boundary areas is quite important. Another COVID-related study, this came out of another multinational team looking at the changes in the canals around Venice from before versus during the COVID lockdowns. You might have seen news stories that said the canals around Venice cleared up during the lockdowns. That was true. You might have also seen stories about things like dolphins or porpoises returning to the canals. That part was false. But you were able to actually see how much the canals changed from the lockdowns from space, which was pretty incredible. So this is a chart showing the amount of total suspended solids in January and February leading up to the lockdowns, and then March into April during the lockdowns. The amount of total suspended solids in the water decreased dramatically due to drops in the amount of boat traffic. And then visually, you could also just see the difference in the water from the lack of turbidity from the boats not being there. And they were also able to do a little bit of rudimentary bathymetry as well, down to about 15 meters in certain areas because the water had cleared up so much from this lack of boat traffic. This is a study out of the University of British Columbia. The idea of the effect of green space on childhood development is a little bit controversial in social science, but we've seen some of this applied to PlanetScope combined with Landsat data in a few different studies. There have been multiple studies showing that exposure to green space like parks and forests has benefits in early childhood development, like improved memory and academic performance and fewer behavioral problems. So this group at UBC monitored about 30,000 children in the Metro Vancouver area from birth through kindergarten, provided they lived in the same postal code through that entire time period. And they used NDVI, Normalized Difference Vegetation Index, so measure of vegetation health, from PlanetScope and Landsat in these postal codes to estimate the amount of green space exposure that these children had, and found positive effects on their development. Some of this is thought to be related to things like lower noise pollution and lower air pollution exposure in these early developmental years. Being able to combine imagery from space with the same dates that you collect data like this on the ground, like in the atmospheric science study, and in some cases, this green space exposure study, has a lot of power to do this sort of modeling work. And this is a study out of George Mason University, led by Ed Otten, where they were looking at cell phone adoption metrics across different countries in Africa. So in this case, governments and mobile network operators have trouble figuring out where they should invest in infrastructure in developing regions where the demand is unknown because they don't have a good idea of whether those investments are going to pay off or not. So Ed Otten and his grad student, Jatin Mathur, used PlanetScope data combined with World Bank surveys across Ethiopia and Malawi to look at cell phone usage. They picked these two countries because Ethiopia has the fastest growing economy in Africa, whereas Malawi is one of the poorest nations in Africa. And so they were kind of taking them as two end members. They fed these results into a convolutional neural network, and they found that looking at these adoption metrics was a lot more accurate when they were looking at combining PlanetScope data with World Bank surveys compared to more traditional surveys of things like population density or nighttime luminosity when looking at things like affluence of different regions. And this study is one of our favorites within Planet because it's something that is very easily relatable to from space. We all know what a walrus looks like. Unfortunately, walruses are coming ashore in places like Alaska more often and in larger numbers due to the loss of sea ice from climate change. So usually when they go out to feed, they will then haul themselves out onto sea ice to rest and then go back to hunting again. But since the sea ice isn't there, they're having to come on shore instead. Unfortunately, walruses are easily scared. And so things like human activity, so boats coming by, airplanes flying overhead, even drones flying overhead, can trigger walrus stampedes back into the water. And this can kill hundreds of walruses at a time, especially like young walruses that are smaller because they're going to be more easily trampled. Being on coastal lands also puts them at higher risk during oil spill events as well. So Tony Fischbach and David Douglas from the USGS looked at PlanetScope along with a few other data sets to try to do near real-time monitoring of the location of walrus colonies. Their eventual goal is to create a walrus alert system that basically says, hey, stay away from this particular area because there are walruses here. They were able to look or visualize quite effectively using all these different data sets where the walruses are, looking at things like the color difference between the beach areas with walruses on it versus not, because obviously at 3 to 5 meter resolution, you're not resolving individual walruses. You can't see some of the individual walruses here in his drone imagery, which is pretty cool. Even though this should be about Planet, I thought the coolest part was that walruses actually have a radar signature, which makes sense, but it's not something I ever would have thought of because I'm used to thinking of radar on Mars for looking for ice. But walruses have a radar signature that is quite dramatic from space, which is pretty cool. So if you're interested in using planet data for your research, how can you access it? Well, through the NASA Commercial Smallsat Data Acquisition Program, or CISDA, you can access all of our PlanetScope imagery as well as all of our rapid eye imagery. This is made available to anybody who is doing research in specifically funded by specifically funded agencies, and we'll see that on the next slide. So through this program, you can access all the PlanetScope data with a 30-day latency on the access, unless you're doing some kind of time-sensitive research, like looking at an active natural disaster. This was something that NASA asked for. Each user is given an initial quota of 5 million square kilometers. If you don't have a good concept of how much that is, it's like 2.5 times the entire area of Alaska. So it's a lot of data. And if you need more than that, all you have to do is ping us and NASA and say, hey, this is what my research is. I need more data. And we'll say, cool, here, we'll upgrade your quota. Through this program, anybody whose research is funded by any federal civilian agency or the National Science Foundation qualifies for access. So this could be NASA, USGS, NOAA, Department of Energy, USDA, anything that doesn't fall under the Department of Defense or the intelligence community can use this data for non-commercial, non-operational scientific research. This includes folks at universities, private labs, national labs, and even commercial companies if their research is funded by one of these agencies. So assuming all of you are affiliated with UW in some way, you can access data through this program if your research is funded by one of these agencies. To sign up is really simple. You just go to go.planet.com/NASA and there's apply now button on the page. It will take you to a form on a NASA website. They actually process the applications on their end. It takes them about 2 to 4 weeks, so it's a little bit slow. But in 2 to 4 weeks, you will receive an email from Planet with your login information, and then you can go to planet.com/explore and see your account there and start downloading data. So once you've gotten that information on how to log in, you can just immediately start accessing the data. But what if your work is not funded by any of these agencies? Well, we have other options for you. Our other main option for folks at universities is Planet's Education and Research Program, or ENR program, and this is available to anybody at a degree granting institution anywhere in the world. Very similar types of access to the NASA program. You can access PlanetScope data, rapid eye data, as well as some of those base map products, those mosaics that I mentioned before. But there's a lot smaller quota there. So if you are looking for free access, we have a basic version of the program that gives you 5,000 square kilometers of data for free per month, and it resets at the beginning of each month. The key here is that there are not any restrictions on what you can use the data for, really, as long as it's non-commercial scientific research. It doesn't have to be funded by any specific agency. You can use it in classrooms. You can use it just to play around with. You can use it for whatever research you want. It just has a much smaller quota. If you need more data than that, we do have a departmental option and a campus option that provide 15 terabytes and 100 terabytes worth of data, respectively. So that's an option as well if you have a group where you need way more than 5,000 square kilometers of data per month, and you don't happen to be funded by a federal agency where you might get access through the NASA program. We also have some other programs. If you have any colleagues in Europe, we have an agreement with ESA called EarthNet, where anybody based at an ESA member state or Canada or China can apply for access through the ESA website. This is a proposal-based process, so you actually have to kind of write a research proposal and say what data you need. We also have a program called RISA, which is through the German Space Agency, specifically for German researchers. So if you happen to have any collaborators in Germany, that's another option for them. And then the Norway International Climate and Forest Initiative, or NICFI, that I mentioned before. So this is specifically tropical base maps over the forested areas in the tropics, freely available to anyone in the world, as long as you are doing forest conservation work. So that there's just an application at planet.com/NICFI, and you can fill that out and then immediately start accessing the data that way as well. We have 5 different ways to access data depending on how proficient you are with command line interface and APIs and how much data you need to download. The main way that most people interact with our data is Planet Explorer. This is best for downloading less than 100 images at a time and just kind of doing like visual checks of coverage and seeing what the images look like. This is just planet.com/explorer. The links here are actually for the documentation that goes along with these things. It's pretty intuitive to use. It's if you've used anything like Google Maps, it's pretty straightforward. So once you have a login, you can log in. It won't ask you for this many steps if you're not a Planet employee. And it will take you to this map interface here. So you'll get kind of a generic base map that's a couple years old at this point, but you can search for your locations here, very similar to Google Maps. It will automatically zoom into where you searched for and give you the most recent results. Looks like it's been pretty cloudy in Seattle, unsurprisingly. And then as you click on these, it will render them in real time on the map. If we can find a day that was not super cloudy. Oh, here we go. Okay, so here's an example from October 16th. You can click here and see that there were 2 separate satellite passes that went over on that day. And here it will show you all the individual scenes that intersect with the area of interest there. You can say that you want to order them. You can either download them directly to your machine, or you can do some hosted analysis in Explorer. That's more for folks that are not very technically inclined. It doesn't have a lot of capability built in. You can do some quick visualizations of things like normalized difference vegetation index and normalized difference water index, but probably for any scientific application, you're going to want to download the data. So if you click continue, give your order a name, and then it will give you a bunch of different options. So if you want surface reflectance data, top of atmosphere, radiance, 4-band versus 8-band. We also have unrectified assets. If you want more basic versions of the data, you can decide what you want here. Click continue. You can decide if you want to clip the imagery to your area of interest or not. This will save you on your data quota, especially if you've got that basic education research account. And then here's the button to harmonize to Sentinel-2. Once you click order, it'll pop open this tab here and show you everything that you've ordered for the last 90 days. So you can go in and download those here. It'll send you an email automatically when your order is done, which will take you to a zip file of all the images. You don't have to sit here and wait for it. You could just wait for that email. Generally, you'll get it within like less than half an hour, depending on how many images were in your order and how recently they were acquired, because they have to be activated from the cloud and then zipped up. You can also manually draw an area of interest. So if you don't want that auto box, you can do something like this. You can also upload an area of interest. So if you have a KML file, GeoJSON shape file that you've exported from ArcMap, something like that, you can upload that here as well. There's a bunch of other options here, things like you can do some imagery comparisons. You can make, you can take screenshots of the data. You can make time lapses that will create videos in this tool we have called Planet Stories. If you want to learn more about this, if you go to university.planet.com, there's videos on how to use all of the features in Planet Explorer there. We also have plugins for both QGIS and ArcGIS. And these are basically like running Planet Explorer inside each of those applications. So the functionality is pretty much the same. The interfaces look very similar, but this way you can bring the imagery directly into your projects. We also have a command line interface. If you're comfortable using a command line and you want really fine-tuned controls, or you want to download huge amounts of data or set up subscriptions. And we have a data API, which is great if you're really proficient in Python and working with APIs. This is a really great way to set up a lot of custom tools, download custom band combinations, create different band combinations on the fly. So say you only want to download an NDVI product, you don't want to download the images behind it, you only care about NDVI. You could do something like that through the API. If you're interested in learning more about using the APIs, we actually have a free webinar coming up on Friday at 8 a.m. Pacific about leveling up your science with data APIs, or sorry, with the Planet APIs. We actually have multiple APIs that you can work with through us. This is a really great team, our developer relations team. So I definitely recommend checking out if you're interested in learning more about this. You can register to get the Zoom link at go.planet.com/levelup. So I like to leave everybody with the question at the end of these presentations. What would you do if you could see daily change of anything, anywhere in the world? And with that, if anybody has any questions about planet data or the satellites or research or any of these access pathways that we talked about, I'm happy to answer any of those you might have.
Thank you, Tanya. This was really great. I'd like to see everything. Please use the Q&A button to tell us what would you like to see in planet imagery, and if you have any other questions for Tanya. I am myself mesmerized by the high spatial temporal resolution of planet imagery. Here's a question from Dave. I'd like to know if the constellation interferes with Earth-based observational astronomy.
That's a good question that we get pretty often. Our satellites are not as large or reflective as satellites like Starlink, for example. So it hasn't been something that's really come up yet. We're also not planning on building a mega constellation like you hear about from some other companies. Like the number of satellites that we have right now is about enough to do the level of imaging that we want to do. So we're not going to have like 10,000 satellites in orbit. You know, a couple hundred is enough to do the job.
Thank you, Tanya. This is a question that's not related to the planet imagery, but it's about figures and animations of the things you showed us, that they look amazing. And I'm guessing I know the answer, but I would like to invite you to tell us about the figures.
Some of them, if it's things like this slide right here, like these visualizations, full credit goes to our amazing data viz team at Planet, led by Rob Simon, who's a former NASA Goddard employee of 20 years. If you've seen like the iconic like blue marble image of Earth, Rob Simon created that. It was the old iPhone wallpaper years and years ago. Him and his team just work magic with the images. From the scientific applications examples, other than the Milne ice sheet animation, most of those were figures from the papers by the authors. So full credit goes to them there.
I'm curious, what are the plans for next constellations? Like, what are the bands are you planning on adding, or is there a plan to add a thermal band in the future?
So right now we're working on two main constellations. One of them is called Tanager. We name them all after birds, if you're sensing a theme here. So Tanager is going to be our hyperspectral constellation. This will be about 400 to 2,500 nanometers, specifically designed to look at methane emissions as part of the Carbon Mapper Coalition. So the methane product will be something that is freely available as a public good through Carbon Mapper. And then the rest of the bands you can access through Planet. So we're working on this as a combination partnership between Carbon Mapper, JPL, and Planet. So we're really excited about that. The first two of those satellites should launch next year. The final constellation is going to be somewhere around 30 satellites. And then we're also working on another constellation called Pelican, which is the replacement for the SkySat satellites. So they are getting close to their 10-year lifespan. And so we're looking at how to replace those. I don't remember how much we've publicly announced on the specs of them yet, so I will not say too much to be safe, but they will be comparable to what you can get from SkySat.
Mm-hmm. And the science applications would be similar as well.
Between Pelican and SkySat, definitely. Tanager is definitely going to open up a lot more opportunities in terms of things like atmospheric science, more detailed agricultural studies. If there's anything that you're interested in working on, anybody on the call where you might want to use hyperspectral data, let me know. Actually, we're starting an early access program for researchers to play with some of our airborne synthetic data to kind of put it through its paces and see if you have any feedback there. We are also planning the what is going to replace the SuperDove satellites. So what is the next version of the PlanetScope constellation going to look like? And we're always open to feedback from the research community in terms of like, what spatial resolution do you need? Are there any limitations to the current data that would be beneficial for us to change for you moving forward? Are there bands that we don't have that you would like to see? Things like that. So if you have any input there on what you would like to see the future daily scan to look like, definitely let me know. We're totally open to discussions about that.
Excellent. Can you tell us about the spatial or temporal resolutions of those? Or that's still a work in progress?
That's still a work in progress, kind of looking at what the community is asking for. So it would definitely not be worse than what we have now, the 3 to 5 meter. But we're looking for like specific examples of like, what resolution do you need to do a specific thing? So kind of like making a science traceability matrix for a NASA mission. We're basically doing that right now for looking at what the next PlanetScope satellite should look like.
Is planning a constellation for Mars? Good question.
I think I get this question a lot because everybody's like, wait, aren't you a Mars person? What are you doing at Planet? I certainly would love to see Planet send a constellation to Mars. And Will Marshall, one of the co-founders, likes to say we called it Planet and not Earth for a reason. If you look at the Planet logo, actually, I wonder if I have the full logo on a slide somewhere. Oh yeah, here we go. So the circle here is meant to be Earth and the dot here is meant to be the moon, because Will Marshall is very, very excited about the moon. So that is definitely something that he's interested in. Maybe we'll expand in the future, who knows? Oops, sorry, I didn't mean to go full screen there. This, in case anybody's interested in the Tanager information, this is some of the comparison of what we're looking at with Carbon Mapper versus, sorry, with Tanager. We've changed the terminology recently, how these two compare. Here's a little video of that constellation. So this isn't going to be like a full global map every day with hyperspectral coverage. That would be a lot of data and a lot of satellites required to do that. But you will get 30 meter resolution at different repeat rates, depending on how many satellites we've built up into the constellation at that point. So like I said, phase 1 is 2 satellites is kind of the demo with JPL. And then phase 2 is when we build up to probably around the 30 satellite range to get increased coverage.
Very cool. You mentioned the start date. I forgot. Maybe you did for the new constellations.
For the hyperspectral one, they're going to launch sometime next year. I don't know if we've announced the launch date officially yet. The Pelican satellites, I think, will probably be launching in 2024. But I don't think we've announced like a firm launch date for that either.
Well, thank you. And speaking about launch dates, there's an end date to the satellites too. And there's a question from Alan. What is the deorbit methodology at the end of life? And when a new satellite version is deployed, does it replace older ones or destroy it as existing satellites expire?
So in terms of deorbit methodology, the Dove and the SuperDove satellites don't have any propulsion on board. And so they just slowly deorbit based on their orbit altitude and then burn up in the atmosphere that way. So we're not actively doing anything with them. With the rapid eye satellites, since they had propulsion on board, we actively lower the orbit altitude so that they would burn up. We'll do the same thing with the SkySats since they have propulsion on board as well. When we put up new versions, right now, it's a little unusual that the whole constellation is all SuperDove satellites. Before March of this year, it was actually a mix of the Dove Classics, the Dove Rs, and the SuperDoves. They were all operating at the same time. So any satellites we had that were still operational and collecting valid data, we would be collecting data from all of those. So it's not like we replace the whole constellation each time we do a launch. It's okay, we'll replenish a certain number of satellites to kind of maintain the continuity of the amount of coverage that we had before, and also like implementing new features that we might have. So we did have a time period there where we had 4-band and 8-band satellites operating simultaneously, but right now we've deactivated all of the older satellites so that we could focus on the Super Dove ones. So all the coverage that you're getting right now is the 8-band coverage.
Excellent. Is there another question? I think this is the last one we're going to take today. Do your satellites navigate over government restricted locations? Are there any countries that don't allow your satellites to navigate over their landscape?
So we don't have any restrictions placed on the data. This has actually come up a few times in news stories for investigations. Like there are certain places where people have gone to look at data in Google Earth, and the data is covered by a mask or it looks blurry for some reason. And then the journalists or the researchers will come and look at Planet data to see what's actually going on. So there's a democratization of the access to the data in that aspect. Anybody can access data anywhere, with the caveat that we do have an ethics board internally. So we make sure that we're not like selling data to bad actors. We're trying to keep it out of the hands of people that might be using it for nefarious purposes. And obviously we don't do business with any countries that are currently under US sanctions. So we can't do any business that way. But there aren't any restrictions in terms of like where you as a researcher can access data. You could download data over anywhere in the world. There isn't any place that we are actively not imaging because of any type of government restriction.
All right. Thank you, Tanya, very much. That was wonderful today. Thank you, all of you, and we'll see you next time.